Thank you for joining us today. On today's Engineers Newsletter Live program, we'll be discussing electrification of HVAC systems, often referred to as decarbonizing. Many customers and municipalities throughout the United States and the world are taking action to reduce their carbon emissions. One of the tactics they're using that affects the HVAC industry is the reduction or removal of natural gas for heating. This means our industry will face the challenge of heating our buildings with reduced amounts or no fossil fuel. This E&L will cover the motivation to electrify, areas currently affected by this trend, and the potential products and systems to meet electrification needs. To walk us through the discussion, we have Dan Gentry from our Applied Product Support team and Charlie Jelen from our Applications Engineering team. Charlie's going to start us off.
I'm going to cover three sections to start the program. First, we'll provide some background on the topic of decarb and electrification. Next, we'll discuss heat pump design considerations, and then talk about some potential product solutions. We're going to start with some basic definitions, starting with the terms that we hear most often when we talk about this topic. First is decarb, which is short for decarbonize or decarbonization. Decarb is the process of reducing or eliminating carbon emissions. And there are many ways to reduce carbon emissions in HVAC systems. One avenue that is being pursued is electrification, which is a second term. It means using electricity in place of burning fossil fuels in your building. An example would be heating your building with an electric heat pump instead of a gas-fired boiler. Now, electrification by itself will not help reduce total environmental emissions. So why are we going after it? Why are we trying to electrify our buildings? The answer is renewables. The hope is that renewable energy sources power the majority of the electric grid in the future. So all electric buildings and utility grids powered by renewables is one path for a sustainable future. But before we talk about the future, we need to address some of the concerns of today. And one question we get asked a lot is, why is burning fossil fuels at the power plant better than burning fossil fuels in my building? To help answer that, we put together a little example. We're going to compare the carbon emission totals for a couple different building and grid scenarios. First, we'll look at a 100,000 square foot commercial office building that uses both gas and electric energy sources to heat, cool, and power the building. We picked a building in the upper Midwest that uses the RFCW E-Grid subregion. This area covers multiple states, including large sections of Illinois, Ohio, and West Virginia. To come up with an energy consumption total for this example, we used the U.S. Energy Information Administration Commercial Buildings Energy Consumption Survey results, commonly referred to as CBECS for good reason. It shows that commercial office space consumes about 80 kBTUs per square foot. So for our 100,000 square foot office building, that means we'll consume about 8 billion BTUs of energy. Also from CBECS data, we can get an idea of the split between natural gas and electricity usage. Since the building is located in a heating climate, we assumed a slightly higher than average usage of natural gas at 30%. But before we calculate the carbon emission for this building, we need to understand the difference between site emissions and source emissions. Site emissions will be the emissions from burning fossil fuels at the building itself, typically to heat the building, heat potable water, or for cooking. Source emissions are emissions associated with burning fossil fuels at the power plant to generate electricity. Source emissions will be different across the country based on the mix of generating sources, which are predominantly coal, natural gas, nuclear power, and renewables. Okay, back to our example. We can calculate the site carbon emissions by converting 2.4 billion BTUs of natural gas into carbon emission equivalents, which equates to 140 tons of carbon. Now, the other 70% of this building's energy was provided by the electric utility, the source. For the RFCW subregion, the mix of energy sources that power the grid are shown here. 33.5% of this grid's energy was provided by carbon-free sources, such as hydro, wind, nuclear, and solar. 44% was from burning coal, and the last 22% was from burning natural gas. The eGrid average carbon emission rate for this region is 1,166 pounds of CO2 per megawatt hour of production. And this does include 4.8% of average grid loss on the system. So using the data, the source carbon emission calculation comes out to 957 tons of CO2. This calculation is based on the average emissions for the utility grid and does not account for marginal or non-baseload emission rates. All right, here's the summary of what we've covered so far. At the bottom of the table, you can see we added both site and source carbon emissions to get a total of 1,097 tons of carbon emissions. We're going to consider this our baseline for an average building in operation today. Next, let's look at the impact to carbon emissions if we switch the building to utilize all electric power. For heating, let's assume we switched from burning natural gas on site to using electric heat pumps. It's obviously a lot more complicated than that, and we'll get into some possible product solutions in a little bit. But for now, we'll assume we figured out how to electrify the building. We'll also assume these heat pumps are on average 3 times more efficient than gas-fired heating equipment. This value is going to change based on your climate. Warmer climates will provide higher heating COPs, while colder climates will yield lower heating COPs. So the total electricity consumption, for our example, will increase because we're heating and cooling with electricity. But the total power consumption went down because we're using more efficient technology. The site carbon emissions are eliminated because we're no longer burning fossil fuels on site. We'll assume the same utility generation mix as the previous example. So calculating the source carbon emissions, we get 1,094 tons of CO2. That means our total emissions went down slightly from the previous example. The common question we get at this point is, why didn't the emissions drop much further? Well, the makeup of the fuel that powers this specific utility grid is less efficient than burning on site. But if you move this building to a different grid, you'd get different results. Like I said at the beginning, electrification by itself is not going to lower total carbon emissions. We also need the grid to be powered by more renewables. So let's look at that example. We'll fast forward to 2030 and go back to our original gas-electric building. We'll assume the energy draw from the building is exactly the same. But the mix of energy supply for the power plant has changed. We'll assume the amount of carbon-free sources has doubled from 33.5% to 67%. Coal's contribution has dropped to 10%, and natural gas is about the same at 23%. The site carbon emissions will be unchanged from the original alternative. This was just to keep the example simple. It's possible that by 2030, gas-fired equipment will be more efficient and therefore have a lower emission rate. On the source side, and with the new energy mix, the source emission is calculated to be 404 tons of CO2. So that's a 63% reduction in source CO2 from the previous example, and a 50% reduction in total carbon emissions down to 544 tons of CO2. For the next alternative, we'll look at an all-electric building on our example grid in 2030. Again, the site carbon emissions drop to 0 because we're not burning any fossil fuels on site. The source emissions are calculated at 462 tons of CO2. So this provides a total carbon emission reduction of 58% from the first alternative. Now, one thing to note, In our example, we assumed that this specific grid was able to double the amount of carbon-free energy in the next 10 years. And that might seem like a lofty goal. However, there are a lot of utilities that are striving to exceed that mark. Xcel Energy is pushing for 80% renewable energy by 2030. Con Ed said they'll achieve 100% clean energy by 2040, and SG&E is already at 85% renewable energy. All right, so let's run our example building with 85% carbon-free sources. To go with that 85%, we'll assume a 5% coal contribution and a 10% natural gas contribution. Using this mix and calculating the total emissions, you can see they go all the way down to 213 tons. That's an 81% total emission reduction from the baseline. So hopefully this helps answer the question of why are we electrifying our buildings? The main reason is the thought that the grid will become heavily powered by renewables. And if you're burning fossil fuels on site, you won't be able to take full advantage of that renewable power. Next, we want to talk about where in the country this is happening. The simple answer is everywhere. There are companies across the world that are taking it upon themselves to reduce their carbon emissions. According to Natural Capital Partners, 23% of the global Fortune 500 companies have climate-related goals. That 23% accounts for a total revenue of $8 trillion and 18 million employed people. Companies, including Trane Technologies, are going after similar emission reductions. However, to get the masses to adopt decarb and electrification, local, state, and federal policy of some kind will likely be needed to move the needle. And we already have cities and states that are moving in that direction. Here is a map showing cities across the US that have emission targets of either 80 or 100% emission reductions by 2030 to 2050. In fact, 18 of the top 20 most populated cities in the US have set some type of quantifiable emission reduction target. Obviously, some cities are moving faster than others, so the amount of pressure you're feeling to change your traditional HVAC designs will be different across the country. Cities and states are also taking very different approaches on reducing carbon emissions. Some cities are banning new natural gas hookups, like Berkeley in California. Others are providing incentives for all-electric designs and heat pump products. And still others, like New York City, have created a carbon emission cap that impacts large segments of the city. This cap in New York, known as Local Law 97, is one of the first large-scale emission programs in the US. Now, there is some potential this type of program gets copied in other cities, so we thought we'd take a minute to explain how the carbon cap is going to be applied. So first, you'll calculate your building's carbon cap, and this is done by multiplying the square footage of the building by the building type emission factor. That factor is laid out in the law for a handful of different building types. Next, you need to determine your building's emissions. This is done by multiplying your building's different energy consumers by emission factors. The law defines 5 different consumption types: electricity, natural gas, district steam, and number 2 and number 4 fuel oils. If your calculated building emissions are under your calculated cap, you're in compliance. If you're over the cap, the owner would be assessed a penalty of $268 per ton of CO2. The first year of penalties will be handed out in 2024, and the cap has the potential to ratchet down every 5 years until 2050. Now, this was a simplified explanation, and there are many caveats associated with the calculations, including renewable energy credits, distributed energy resources like energy storage, and greenhouse gas offsets. And this is just one example of a city pursuing carbon emissions. Every city and state will have its unique circumstances that will dictate how your specific projects will pursue carbon emission reductions, if at all. Okay, so that was the background. That's why we're talking about this topic today. But next, we want to get into heat pump design considerations. Heat pumps are not a new technology. They've been around for a while. But with designers pursuing all-electric buildings, heat pump technology will be applied now and in the future more than ever before. And when our industry talks about heat pumps, we're typically referring to reversing heat pumps, meaning we control the refrigerant cycle to generate either heating or cooling outputs. The mechanism most often used to do this is a reversing valve, called such because it reverses the flow of refrigerant through the heat exchangers depending on which mode of operation it's in, either heating or cooling. Shown here, you can see the refrigerant always flows through the compressor in the same direction. It's the reversing valve that coordinates flow direction through the system. Heat pumps are generally applied in 4 high-level buckets. First category is air-to-air heat pumps. These pull BTUs from the ambient air and transfer them directly to the conditioned air stream. An example of an air-to-air heat pump is a rooftop unit or a VRF system. The next bucket is water-to-air heat pumps. These pull BTUs from a water source and move them to a conditioned air stream. A common example of this would be a water source heat pump. The third category is air-to-water heat pumps. An example would be an air source heat pump chiller. And then lastly, water-to-water heat pumps. These move BTUs from one water stream to another water stream. Now, as we're talking through heat pump products, there are a couple considerations to think about for any heat pump application. The first one we'll cover is the concept of cold climate heat pumps. This applies to air-to-water and air-to-air heat pumps because the unit is using ambient air as a source or a sink. Cold climate operation simply means, can your heat pump operate in heating mode in cold conditions? And there isn't really a number associated with what cold climate means. However, our industry commonly refers to cold climate as anything below the lowest standard rating point, which is 17 degrees Fahrenheit. When designing a heat pump system, the ambient heating minimum is a critical value. Product limitations such as minimum ambient lockout must be understood to design a resilient and reliable system. Now, oftentimes, designers use extreme annual temperatures to design air source heat pump systems instead of average annual design conditions. And the difference can be seen for this example city using ASHRAE 2017 weather data. The average annual heating design for 99.6% is 13.5 degrees. But the extreme annual design for the previous 5 years is 5.8 degrees. Here is a map showing various northern cities and their respective 5-year heating minimum values. Each city will have its own unique heat pump operation based on different product capabilities. One more topic on cold climate is the sizing of heat pumps for both capacity and electrical. We typically say that heat pumps are 3 to 4 times more efficient than electric resistance. This is true, but only when the ambient temperature is mild. As the temperature drops, the story changes. Let's look at a graph of generic heat pump performance. This is meant to show general trend, not predict any specific heat pump performance. The red line is showing you the heat pump power input for different ambient conditions. You can see that as the temperature drops, the heat pump needs to input more power. If we add in capacity, you'll see the opposite is true. As the temperature gets colder, we get less capacity out of the heat pump. At 60 degrees, you can see the input power is 10 kW, and the capacity output is 40 kW. This yields a coefficient of performance, or COP, of 4. But as the ambient temp drops, you can see the COP drops as well. So the question for the designer is threefold. Number one, what is the minimum operating temperature for the equipment? 2, what is the capacity output at that minimum ambient? And finally, 3, what is the kW input at that minimum ambient? With this info, the designer can understand the limitations and the energy profile of their heat pump design. All right, next we want to talk about defrost. When a heat pump unit is in heating mode, the outside coil is pulling heat from the outside air. Another way to think about it is that the outside coil is cooling down the outside air. And if that coil temperature is below the dew point outside, condensation forms. If the coil is also below 32 degrees, you can start to freeze that condensation. Too much frost in the outside coil can degrade performance and potentially put the machine into a lockout mode. To make sure that doesn't happen, heat pumps employ a defrost mode to melt that frost before returning to normal operation. The reason defrost needs to be investigated up front is because some defrost modes require 100% of the unit's heat to be used to defrost the coils. That means no heat is being sent to the space during defrost mode. And making the situation potentially even worse is if the building also requires ventilation. You'd then be sending cold air into the building and pulling warm air out. This could obviously have a real negative impact on occupant comfort and should be considered in system design and control. The last consideration we have here is using dual fuel or auxiliary fuel options. Dual fuel means the product is a heat pump, but also has a gas-fired heat exchanger as a backup. Auxiliary fuel is having a heat pump that also has electric resistance as a backup. This becomes a nice option for applications in cold ambient, where the heat pump either loses capacity or can't operate in cold temperature. Dual and auxiliary fuel would also be a potential way to limit defrost impacts to the occupied space. For our last section, Dan and I are going to walk through some potential product and system solutions.
The first product category we'll look at is split system heat pumps. Called a split system because the condenser coil and compressor are in one package, the outdoor unit, and the evaporator and fan are in another, the indoor unit. Refrigerant lines are then connected in the field to match the system together. These end up looking a lot like most ducted residential systems. Cooling-only versions of split systems can range in sizes larger than 100 tons. However, heat pump split systems are typically 20 tons or less. Applications best suited for split system heat pumps would be the light commercial space, small retail, small office, and classrooms. When designing with these systems, ambient minimums are a concern. Most split system heat pumps do not have cold climate capability, so the heating capacity will be reduced or even eliminated when ambient temperatures fall below 32 degrees. To help with this situation, dual and auxiliary fuel options are available from most manufacturers. These systems typically lend themselves well for electrification retrofits. The outside unit is typically in a location that is easily accessible, and new heat pump equipment will have a similar footprint. For the most part, owners and designers replace the line set, refrigerant specialties, and coil. Also worth noting, for any heat pump retrofit, the electrical feed supplying the heat pump should be checked to make sure it can handle the heat pump duty. Next, we'll look at another split system, variable refrigerant flow, or VRF. These systems are probably the most popular heat pump system on the market today. Their capacity per unit is typically less than 40 tons, but they can be linked together to form larger systems. Over the last 5 years, we've seen VRF applications grow in number. Some of the more popular are schools, offices, and any kind of mixed-use space. The flexibility of these systems, with refrigerant pipes running through the building instead of ductwork, make them a good candidate for a wide variety of applications. VRF also offers a lot of capability in terms of operation. Auxiliary fuel is possible with electric terminal heat, and most VRF manufacturers offer cold climate capability with heating operation well below 0 degrees. Another great feature within most VRF products is smart defrost control. There are a couple different ways this is accomplished by different manufacturers, but the end result is the unit goes through a defrost cycle but some heat is still delivered to the zone to avoid occupant discomfort with cold supply air. VRF is an interesting retrofit opportunity, and the difficulty of that retrofit will be based on the existing system. If the building has no air conditioning and you're comparing various systems on ease of retrofit, VRF might rise to the top. Being able to run small refrigerant lines through the building is typically easier than running ductwork through the building. On the other hand, if you're replacing an existing cooling system, say a PTAC, RTU, or any hydronic system, it's likely easier to use a heat pump of the same style instead of retrofitting to VRF. Take a PTAC, for example. It would be much easier to swap that PTAC for a packaged terminal heat pump than going to VRF. One thing to note, with any distributed heating and cooling system, the ventilation system would need to be considered as well. If a dedicated outside air system is used, that too could be electrified with a heat pump.
All right, next we'll start to look at some packaged units. And first is rooftops. These are typically offered with heat pump capability 20 tons and under. Rooftop heat pumps are a great electrification package because the unit can handle all aspects of the system: heating, cooling, ventilation, and controls. Typical applications will be similar to current rooftop unit applications, so classrooms, warehouse, small office, and retail, just to name a few. A limiting factor for many RTU heat pumps is cold ambient operation. Most units cannot provide the needed heating capacities at or below 0 degrees. However, dual fuel is an option from most manufacturers. In terms of electrification retrofits, these units might be the easiest. Assuming you're retrofitting an existing RTU, heat pump RTUs are built on the exact same chassis as the standard units, so the physical replacement is swapping the units out. Unlike split systems, there are no line sets external to the unit, so that's not going to be a concern. However, standard rooftop units cannot be retrofitted with heat pump components, so the entire unit will need to be replaced. Again, with any heat pump retrofit, electrical service must be checked to make sure it can handle the heat pump duty. All right, next is packaged terminal heat pumps. These units are on the smaller scale, mainly because they're only serving the room they're located in. They're typically applied in hotels, high-rise residential, dorms, and long-term care facilities. For backup heat, auxiliary electric resistance is available from most manufacturers. However, cold climate heat pump is not a common feature for most packaged terminal heat pumps. Typical operation is going to be just based on the outside air temp. When the temperature goes below 32 degrees, the heat pump turns off and the electric resistance turns on. For cold climate locations, this means you'll be sizing your peak heating and electrical loads with 100% electric resistance. However, these products are ideal for electrification retrofits. If there is already an opening in the building that contains a PTAC, going with a packaged terminal heat pump with the same chassis is very doable. If the building you're looking to retrofit does not have air conditioning at all, cutting an opening in the side of the building to accommodate a packaged terminal heat pump might be a bit of a hurdle, but potentially a lot easier than other system options.
Water source heat pumps are probably the most well-known heat pump technology on the market today. Typically, sizes are less than 25 tons and can heat and cool multiple zones or single zones. They cover a wide variety of applications, some of the most common being apartments, offices, schools, and clinics. For electrification options, the system can offer multiple forms of dual fuel. The product itself can be supplied with electric resistance backup heaters. On top of that, the condenser loop can be tempered with either electric heat, heat pump heat, or gas-fired heat. This flexibility allows the system to operate in cold climates without issue. In terms of electrification, water source heat pumps have a lot to offer. Since all the heat pumps share a common condenser loop, heat recovery is maximized in the system. Any water source heat pump can provide heat recovery to any other water source heat pump on the system. For retrofit opportunities, water source heat pumps have two opposing categories. If you're looking to retrofit a building that has no air conditioning, water source heat pumps might be one of the hardest systems to get into the building. You need both a common water loop and terminal equipment run to each zone. This makes it quite restrictive. On the other hand, if you have a building that already has water source heat pumps and uses a gas-fired boiler for loop tempering, this offers a potential target for electrification. That boiler can be supplemented or replaced with a heat pump chiller or chiller heater. Since loop tempering can utilize mild hot water temps, air and water heat pump technology available today is well suited for this application. Before we leave water source heat pumps though, one more note on retrofits. Any hydronic system could be a potential retrofit opportunity for water source heat pumps. Since there are already water pipes running to each zone, they could potentially be repurposed as a water source heat pump condensing loop. Okay, that's it for unitary, packaged, and split heat pumps. Next, I'm going to take us through products on the applied side. In our discussion of applied systems, we will introduce what an applied system is, describe heat pumps and heat recovery chillers, explore air source and water source products, dive into applications, and end with potential sources and sinks. When we talk about applied systems, we assume that the system contains a centralized chilled water generator, typically a chiller, and a centralized hot water generator, typically a gas-fired boiler. Pumps move the water from the centralized plant through a network of pipes and to the terminal units, often coils. The coils then transfer their energy to the space being conditioned. The water then enters the return line and is pumped back to the central plant. In the coming discussion of electrifying systems using heat pumps and heat recovery, we will look at what these products are and then at several ways to use them to help reduce or eliminate the need for the gas-fired boiler. First, let's talk about a few definitions and create an understanding for terminology when we are talking about heat pumps and heat recovery chillers in applied systems. So what is a heat pump? Heat recovery chiller, chiller heater, and a heater. The names may sound interchangeable, but there are some notable differences when it comes to equipment technology. Let's look at heat pumps. The term heat pump is often used in our industry to describe any unit that is used to provide heat. While this is a common term, we can better define this as there are different types of equipment choices that can be made using this technology. In simple terms, a heat pump is a unit that contains a reversing valve in the refrigeration circuiting, which allows the evaporator and condenser to switch roles. So when we look at heat pump heat exchangers, we use the terms source and sink instead of evaporator and condenser to describe where we are either absorbing energy from or rejecting energy to. Because of the switching of modes, these units can be considered reversible. Heat pumps can come in a wide range of sizes and are available in water source and air source versions. In this slide, we are illustrating a heat pump operating in cooling mode. This operation is just like a chiller producing cold water for a cooling load and rejecting the heat absorbed to a sink. Shown here is an example of a heat pump rejecting heat to the ambient air. This now shows the heat pump operating in heating mode. The reversing valve has now changed positions and the source and sink have switched. We are now pulling heat out of a source and providing heat for the load. Now the heat pump is absorbing heat from the ambient air. Ideal applications would be buildings that cool in the summer and heat in the winter, like a school, for example, or a multi-use high-rise that has to heat during a cool morning and provide cooling as the day warms. Now that we understand what a heat pump is, let's take a look at heat recovery chillers and heaters. A heat recovery chiller is simply a chiller that is recovering some or all of the heat of rejection to be used for heating purposes. Unlike a heat pump, where the purpose is only to heat or to cool, a heat recovery chiller is used to provide both heating and cooling simultaneously. The primary application of a heat recovery chiller is cooling and recovering heat as a byproduct. Common heating uses would include, but not be limited to, comfort heating, laundry, showers, pool heat, and sterilization. The piping layout shown here will be considered preferentially loaded. This means that the heat recovery chiller needs to make the system chilled water temperature because it is sending it directly to the load. In this case, we get what we can get out of the condenser side for heat. Heat recovery chillers can come in numerous sizes, configurations, and compressor technologies. In these examples, we are focusing on water-cooled heat recovery chillers. Next is the heater. A heater is the same machine as a heat recovery chiller, but is applied with heating being its primary function and chilled water is the useful byproduct. Here we see the heater piped in a sidecar arrangement. These units would control to a heating water set point and get what they get on the chilled water side as the cold water is being sent to the return of the main chiller plant. Common uses would be the same or similar as heat recovery, but the load would dictate which application would be appropriate. Our last water source unit is the chiller heater. Again, these units are the same as a heat recovery chiller or a heater, but are applied and controlled in a different fashion. The chiller heater can be controlled to provide heating or cooling as a primary function. Again, these units do not contain a reversing valve. The control function is dependent on the application need at a particular point in time. With some basic terminology covered, we can now look at some products and how we can use them in an applied system. First, we will start off with air source products. Pictured here is an air source heat pump. As the arrows illustrate, one can see the unit uses the ambient air to absorb heat and input that heat into the load water. Pictured on the left would be typical operation in the heating mode. Because this is a heat pump and contains a reversing valve in its refrigeration circuit, it can also reverse modes of operation and provide cooling by rejecting heat to the ambient air, pictured on the right. The construction and design of an air source heat pump is very similar to that of an air-cooled chiller. Pictured here are a few examples. With our understanding of heat pump terminology, we can describe a few major components. The air coil would be considered a source or sink depending on the mode of operation. In the heating mode, the air coil is absorbing heat to be put into the load water. While in cooling mode, the air coil is a sink that is rejecting heat like a chiller and producing chilled water for the load. Variable speed fans then maintain the required operating pressures similar to condenser fans. The controls of a heat pump are again similar to that of a chiller, except the operator can select heating or cooling mode. Air source heat pumps can be found in many size ranges and configurations. So how does the energy contained in the ambient air get transferred to the load water? Pictured here is a generic refrigeration circuit for an air-sourced unit. Ambient air is pulled across the face of the outdoor coil where the energy contained in it is absorbed into the refrigeration circuit. The compressor then adds heat and pressure to the refrigerant. And finally, this heat is transferred to the water in the heat exchanger and pumped to the load. Air source heat pumps can come in packaged or modular configurations. So why choose one over the other? Let's look at some features of both. Packaged heat pumps come in a wide range of nominal sizes and configurations. Mostly utilizing scroll compressors, smaller units are typically a single circuit, where larger units feature dual refrigerant circuiting. Packaged units can be advantageous for larger projects as they can be lower cost at larger tonnages. These units can offer options like low sound fans and pump packages to accommodate site requirements. Modular units are another option as well. Modular heat pumps can offer flexible sizing and footprint configurations, typically offered in nominal tonnages from 10 to 80 tons per module. When redundancy is required, modular units can provide an easy way to accommodate this as they feature multiple independent circuits or additional modules can be included in the array. Because they use multiple units linked together, they can be a good solution for variable flow systems. Options like pump packages and glycol systems can easily be incorporated into a modular chiller assembly. Now we can take a look at a few ways to apply air source heat pumps in an applied system. Our first application example looks at using an air source heat pump to supplement or offload a boiler load. In this system, you can see we simply install the heat pump on the return side of the heating load and preheat the water returning to the boiler, reducing or eliminating the boiler. This is a simple way to electrify a heating system. This application is typically referred to as preheating because the heat pump may not be able to make the higher temperature water needed off of the boiler for the heating system. For example, if the heating system needs 160-degree hot water, an air source heat pump may only supplement this temperature as the current maximum heating temperatures today are in the range of 130 to 150 degrees. For this reason, it is important to understand the heating system supply and return temperatures and verify the heat pump can operate at the conditions we are designing to. The next application we will look at is a water source heat pump system. This system would typically include a cooling tower to reject excess heat and a boiler to provide needed heat, both designed to keep the water source heat pump loop within the operational range of the water source heat pumps. A simple way to electrify the system would be to remove the boiler and install an air source heat pump to take care of the heating needs, formerly done with the boiler. Another benefit of this application is that the heat pump could also provide some redundancy or backup. Let's say the cooling tower goes down or is in poor shape. The heat pump could be operated in cooling mode to make up for this condition. Incorporating this heat pump would typically be as simple as connecting to the main loop, as connections can be made almost anywhere in the piping system. Many water source heat pump loops are designed in the 60 to 90 degree range. Many air source heat pumps would be able to produce these temperatures down to around 0 degrees. Below this ambient, additional heating sources could be required. Let's take a look at a new heating trend. Many new construction heating systems are going to lower temperature hot water requirements to suit the building needs. These temperatures can range from around 90 to 120 degrees, depending on the system design and building location. Many existing heating systems were designed in the 160 to 180 degree range. Lower heating temperatures are significantly more efficient than the higher temperatures of the past, allowing for higher system COPs. For heating systems with lower grade requirements, air source heat pumps can be a great design consideration for electrification. In these systems, an air source heat pump can be used as the sole heating source for the building. Of course, a boiler backup is always an option if needed. Many heat pumps are available today that can provide these lower heating temperatures at an ambient range down to 0 degrees. With so many sizes available, as previously noted, there's quite a bit of flexibility when evaluating this potential system solution. When looking at an air source heat pump for the building needs, in addition to the ambient requirements, defrost mode, as Charlie covered earlier, has to be considered. Shifting gears now, we'll focus on water source heat pumps and heating chillers. Heat recovery chillers do not have a reversing valve and have the ability to control to a hot water temperature, as previously discussed. These units will be as small as a few nominal tons all the way to over 1,000 tons. Our first water source application is heat recovery with a cooling load. In this system, we will have both heating and cooling loads. The chiller could control to either a cooling or a heating temperature. As previously discussed, this application or system would define the requirements for how we would be controlled and applied. So how does one size a heat recovery chiller? This process is quite straightforward. We can examine a load profile to determine what the sizing should be by finding out what the maximum coincidental load is. This graph is for an office building in Chicago. We have a peak load of about 600,000 BTUs and a peak heating load of about 200,000 BTUs. As the table shows, we can see the maximum simultaneous heating and cooling load is about 57,000 BTUs. We can then size our heat recovery chiller to match this load to recover as much energy as we can without oversizing the chiller. What if we need heat but don't have a cooling load, but we do have a source? Our second application example is using a heater to provide heat, but we don't have a cooling need. In this application, we may look at using some other source available. Examples to come. The intent is to only provide heat with the available source. We have reviewed a couple of examples. Now let's take a look at potential sources and sinks for BTUs and where can I use the chilled water made. Please consider that not all sites will have all of these sources available. Rather, these are potential places that energy for heat can be found. The following examples will be brief to simply provide some ideas. Our first example of where BTUs can be found has been around for a long time and is still a great option today: geothermal. A geothermal system consists of a ground source or geothermal loop coupled to the building's HVAC system to reject or add heat to the building as required. The ground loop can come in contact with a large body of water, water pumped from the ground, or a closed-loop bore field of pipes buried in the ground. Pictured here is a vertical bore field. Lakes, ponds, and rivers are common sources to consider as well. Similar to lakes, ponds, and rivers, irrigation systems can be potential sources. Wastewater is another potential source to consider for moving BTUs. Buildings pump out wastewater, and there is heat contained in this water. Specialized systems are available that incorporate a filtration system so this water can be used in a heat exchanger to exchange BTUs. We all know buildings need to bring in fresh air and remove exhaust air, and this air contains energy. However, this energy can also be used as a source to provide heat. One could consider installing a water or DX coil in the building exhaust to recover heat. This exhaust is year-round, and buildings like hospitals can always use heat. How about an air source heat pump? Why not install an air source heat pump in the building exhaust? This way we can pull heat from the building year-round and not even worry about defrost. Another option for finding BTUs is to use thermal energy storage. Let's take an office building, for example. During the heating season in the morning, the building exterior needs heat. You can make ice and store that in a thermal energy tank and use the rejected condenser heat to serve the heating loads. As the building warms up during the day, you can melt the ice to serve the cooling loads. This will be an example of a storage source heat pump application. Our next application example is a little unique. Here we are looking at a building being supplied with district hot water. A heater can be used to provide boosted heating temperatures for higher temperature requirements than what the district heating plant provides. This may be advantageous for smaller or specific loads that need hotter water compared to the rest of the heating system. How this works is we pull district supply hot water through a heat exchanger that is transferred to the heater. The heater boosts the hot water to the temperature required for the load and is then returned to the heater. The heater then feeds the heat exchanger. Essentially, the energy removed from the building is transferred back to the heating plant. This can be a great way to electrify a heating system.
The last segment we're going to look at is potable or domestic water heating. Again, we're going to focus on a couple different ways to electrify these systems. Now, most potable water systems are standalone, meaning the HVAC system and the potable system do not overlap. So that's going to be the focus for the next three products. The first one, and most straightforward, is just replacing your gas-fired potable water heater with an equivalent electric water heater. An electric water heater uses an electric element inside the tank to heat the water. The size of these units can get quite large, typically up to 350 MBH of output capacity, and even higher for some custom units. The control is really simple. Most common is just using a temp sensor and a thermostat inside the tank. The plus side of using this type of equipment is cost and ease of replacement. There are, however, a few things to consider. First, you'll need to make sure you have enough electrical power to run the equipment. If you don't, updating the electrical service to accommodate the equipment could get costly. Second, you might need to add more storage capacity in the tank because the recovery rates of the electric heaters are typically slower than gas-fired. This could cause some space constraints if the existing unit is already tucked away in a basement. Lastly, the efficiency of these units will be comparable to gas-fired units. However, most utilities charge more per unit energy of electricity than for gas, so your monthly utility bill will likely be going up. The second option we're showing here is a packaged heat pump water heater. Called packaged because an air source heat pump is integrated into the tank. The heat pump uses the air around the tank as a source of heat and transfers it into a heat exchanger inside the tank. These units are typically smaller in size, with output capacities up to 60 MBH. The advantage of these units over electric resistance is the energy consumption and demand. These heat pumps will be 3 to 4 times more efficient and will help lower your utility bill. There are a few drawbacks to these units though. The first one is cost, which will be noticeably higher than an electric resistance heater. The second is how it operates in the space. Since the heat pump is using the ambient air around the water heater, it's acting like an air conditioner, sending cold air into the space. So there will need to be some design work to make sure this doesn't impact either the occupied space or the operation of the unit itself. This could also be an opportunity for some spaces though. If you have areas that need constant conditioning, there might be a way to utilize the waste cooling as a benefit. The last technology we'll look at here is a split heat pump water heater. As the name implies, the heat pump in this system is not integrated into the hot water storage tank. Rather, it's typically located outside where it can use the ambient air as a heat source. The size of these units range from 2,000 MBH and below. And there are a few advantages of these split units over packaged. First is capacity. Split units can provide much larger heat pumps for larger scale systems. Second, since the split heat pump is outside, it does not have an impact on the indoor ambient air around the storage tank like the packaged unit does. There are a couple things to consider with these units though. First is the ambient conditions. Now that the heat pump is located outside, you'll need to make sure that that unit can operate in the worst case conditions it's going to see. Some manufacturers can provide operation in cold climates down to 0 degrees or even below. The last consideration is the water lines running between the heat pump and the hot water storage tank. If you're located in a cold climate that sees ambient conditions fall below freezing, the designer will need to take precautions to avoid freezing these lines. Heat trace is a common solution to avoid some of those issues. Now, a slight variation of this system would be to use a water source heat pump instead of an air source heat pump. If you have a common water loop, like in a water source heat pump system, tying into that could provide operational advantages for both efficiency and ambient limitations.
Thank you, Charlie and Dan. Remember to download the handouts, which include a bibliography with resources related to electrification. Today we provided a high-level review of electrification of HVAC systems. Look for an Electrification Part 2 in 2021, where we'll dive deeper into the applications. Ask your local Trane office about next year's complete program lineup. And we're currently working on new opportunities and delivery methods to make these programs more effective and accessible to you. Be sure to subscribe to the Trane Engineers newsletter as well. For those of you seeking continuing education credit, be sure to check out continuing education programs, which include many past E&Ls, all free and on demand. These programs are now located under the self-paced training on Trane.com. Thanks for your time today. We look forward to seeing you next time.